In this lecture, we're going to talk about comets and the Kuiper Belt and the Oort cloud, which are actually very closely related. And this concludes our tour of the solar system, where we went from closest to the sun, farthest out, first talking about the inner planets, the asteroid belt, Jovian planetary systems, and then now we're on these two collections of debris. So the Kuiper Belt, which is around beautiful Keplerian ellipses. They might be chaotic or interrupted by interacting with a planet or the sun. And then where they come from and what they leave behind, which actually includes meteor showers. And so the two regions where comets come from will be the Kuiper Belt and the Oort cloud, which you can think about as outer, icier versions of the asteroid belt. So the same very, very sparse collection of material. But again, as you get farther out from the sun, you're less comprised of rock and metal and more comprised of volatiles and ices, which of course now doesn't mean just water ice. It could be ammonia ice or methane ice, anything that would freeze at about 30 to 70 degrees above absolute zero. So historically, and this is nice because they're, of all of the astronomical phenomena, planets, stars, and comets are actually the easiest to observe. And comets, because of their fixation in the human mind, have been really well recorded in history and generally thought to have some sort of supernatural origin, usually a portent of doom. And this is a really good example of that. This is one small piece of 70 meter or 240 or so feet embroidery called the Bayeux Tapestry, which functioned as a newspaper of the time, so recording a bunch of events in a series of scenes. And this particular scene records a group of people. These are the Normans in North France, and these are the Anglo-Saxons. There's King Harold of the Anglo-Saxons in England. This is the English Channel separating them. Like all pictures in astronomy, it's not to scale. And they all seem to be fixated on this thing in the sky. And this turns out to be Halley's Comet before it was known as Halley's Comet. And at the time, people thought this was a portent of doom. This is Harold being advised by one of his courtiers that, oh no, there's a portent of doom in the sky. And these are the Normans saying, hey, look, there's a portent of doom in the sky. Let's go doom somebody. So they sailed across the English Channel and took over England. I guess it's all about how you interpret the comet, I suppose. But by 1577, when Europe was starting to crawl its way out of the Dark Ages and people were getting more and more interested in what we would call scientific astronomy, none other than Tycho Brahe took observations of a great, huge comet that appeared in 1577. And as well as tracking it, which is good data that people use even to this day to figure out its orbit, he actually did an experiment to show that it was in the heavens instead of an atmospheric phenomena. So if you remember at the time, people thought that the heaven space and the planets were perfect and incorruptible, and nothing would ever change. Stars would always be shining since the day of creation, and only perfect circular orbits could exist. So the idea that there would be this streak that would change in time and mar the heavens was inconceivable to this set of ideas. And what Tycho did is he actually took observations against the background of stars in what's now Denmark on his little party island. And he had one of his collaborators who was in Prague do the exact same thing. And what they saw is that the comet was at the exact same place in both of those positions, even separated by, maybe almost 1,000 miles, maybe a few hundred kilometers. Which means, since you don't see it shift against the background of stars, it must be really far away. So this is this idea of parallax, that the closer something is to you, the more it will shift as you move your position. So they deduced from this that comets needed to be in the heavens, and this actually dealt a blow to this idea that the heavens were perfect and incorruptible. So by 1705, Kepler and Newton had published their laws, and so people knew a lot about the motions of things in the heavens. And the next time a large comet showed up in 1705, Sir Edmund Halley got to thinking and went through the historical record and noticed that there was a similarly great comet that showed up in 1456, 1531, 1607, 1682, and those were separated by on average 76 years. And so knowing what he knew about ellipses and Newton's law, he said, well, if it's going to obey a nice elliptical orbit, it'll also be back in another 76 years. So he predicted that Halley's Comet, what's now known as Halley's Comet, would return in 1758. And this is a contemporary picture of it, so you can see how much of the sky it transgressed. A really beautiful, obvious phenomena. And then you can see a tract released at the time about, comet alarmism, which actually continues to this day. People still get alarmed over comets. Unfortunately for Halley, he made his predictions in the early 1700s, and he died in 1742, 16 years before his prediction came true, and he would have seen what's now known as Halley's Comet return. So these are actually the exceptions, these really nice regular visitors that are in nice Keplerian orbits. And you see a few of them here, and the orbits can actually have anything from very, very short yearly periods to things like Halley's Comet, which is kind of in the middle. It's got a 76-year period, to these comets that, it's only been inferred from one visit. Certain comets actually have thousands to 10,000 year orbital periods, and the only reason we know this is we're so good at calculating Newton's laws that you just need to see it once and then you know when it'll come back a second time. The majority of comets, however, are what you might call one-hit wonders. So a really good example of that is Comet Shoemaker-Levy 9, and this is again an infrared image, so you're kind of seeing heat, really hot there, less hot there. Image of Shoemaker-Levy 9 as it impacted with Jupiter after it was ripped apart by tidal forces. And this would definitely be, a life-ending comet or a mass extinction causing comet if it were to hit Earth. So fortunately for us, Jupiter took care of it. And in fact, since we started observing the sun in great detail, the sun is quite a comet vacuum, and you see hundreds of comets. Now, these aren't big, beautiful, large comets like Halley's Comet. These are tiny little things, but they still grow a tail, and they still come in from the outer part of the solar system. But the sun is sweeping them up at hundreds of comets per year, at the rate that we see them at least. And here's a video of this basically being animated, so you can see the sun eat the comet. And just a little bit of background on this. To make an instrument that observes solar weather, the actual edge of the sun proper, is so bright that you need to put an aperture over it so you don't overexpose the picture. So what this is indicating is this is where the surface of the sun would be, and this is the sun's atmosphere, which all need to be blocked out so you can see relatively dark things like a comet being eaten by it. But lots and lots of comets, and most of them seem to be these one-hit wonders. But they're all comets, and they all have a similar composition. So the next set of questions asked is, what on earth are they made of that they can generate these beautiful tails? And I do say tails, so on Hale-Bopp you can see both of them. So there's obviously one tail here and one tail there, and this has to do with their composition. As pretty as they are, the best mental image of a comet that I think you can take away is, imagine that there's a snowstorm and a large parking lot gets plowed by the plows and they push all the snow into a corner, and then days after the snowstorm, all the snow is gone aside from the stuff in the pile, and the pile has frozen and melted and frozen and melted. So you see these parking lot piles of basically crappy, icy, refrozen snow, but it's completely darkened by dirt and is covered in asphalt and small pebbles. That pile is a pretty good approximation of what a comet is. So in general, this dirty snowball model explains a lot, and we've actually observed stuff being blasted directly off of a comet by spacecraft that were right next to it. So this really is what they are. So if you imagine, dirt and kitty litter, and it's frozen solid because comets generally form really far away from the sun, maybe out past Neptune or farther. And again, remember that volatiles and ices mean things like frozen ammonia, frozen methane, dry ice, frozen carbon dioxide. And as they get closer to the sun, they start melting, and this is the origin of the tails. So specifically, comets actually have three tails, only two of which you can see. when the comet is visible in the sky. The third one we can see later on if Earth's orbit is lucky. So the two tails that are generally visible as the comet approaches the sun are what are called the plasmatail and the dust tail. So the plasmatail is the gas that's released as the comet starts to melt, and is actually also ionized and knocked off by the solar wind. So these are the same processes that strip a terrestrial planet of its atmosphere. The solar wind just knocks gases off. And in this case, you can see the direction of the sun because this is where the solar wind is coming from. So the plasma tail, regardless of which way the comet is moving, is just pushed directly back from the sun. And this is the straight tail, not curved, because the gas that's evaporated off of it is so light. And it's plasma because it's glowing, because it's been activated and energized by interacting with the solar wind. So the second group of material that melts off of the comet as it gets closer to the sun are little particles of dust. So this would be the dirt in the dirty snowball. And you can tell the dust tail because the material is a little bit more massive, will curve away from the comet's direction of motion. So imagine that you're on a skateboard or something and you have a handful of dirt, and as you're rolling really slowly, the dirt will fall, but then it'll also curve away from you. So this is the dust tail, and this would be tiny, nearly microscopic grains of dust. And then finally, there's a third tail that you can't see, and this would be the things that are a little bit larger, like small pebbles and things that are about the size of grains of sand or kitty litter. The larger material will actually just fall directly in the comet's path. So almost like a trail of breadcrumbs showing you where the comet came from. That's the so-called debris tail. So here's a cartoon of an entire orbital cycle of a comet. Far away from the sun, all that's left is what's called the nucleus. This is the rock solid part, completely frozen. And then as it gets closer and closer and heats up, the nucleus will first start to evaporate at the outer edges, and then as it gets close to the sun, the solar wind will blow the plasma tail directly back away from the sun, and the dust tail back and curved in the direction of the comet's motion. So in this case, the comet is moving here clockwise, and the debris tail is, the dust tail is curved away from that. And then finally, as more and more of the comet melts, the larger material will just fall directly in the path of its orbit. So here are a couple of videos. One includes actually a really nice engineered orbit of somebody trying to figure out how to get a spacecraft to a comet to take some observations, and then another animation of this just showing the tails growing as the thing gets closer to the sun. Okay, so how do we know about that third tail? The third tail, which actually doesn't puff up big and bright as the comet comes towards the sun, is actually the origin of meteor showers. So after repeated passes, the comet comes close to the sun, farther from the sun. It's leaving behind, what could be an appreciable amount of its mass in the form of this little material, this sand-sized and kitty litter and pebble-sized set of stuff. And if the Earth's orbit happens to go through that, all of that material will splatter against our atmosphere, kind of like bugs against a windshield if you were driving through really buggy, say for instance, like Kansas night. And this is not a real image, this is photoshopped, but it gets the point across. I'll leave some links to really good high-speed time-lapse images of meteor showers. But if you were to take a nice time-lapse image of a meteor shower, all of the meteors would seem to come from a particular location in space. And what this is the direction that Earth is moving. So Earth is zooming off at 30 kilometers per second in this particular direction. And as it passes through the portion of space where a comet has passed, it actually interacts with the debris tail, and that stuff splatters against Earth's atmosphere, gets really hot, burns up. Even something the size of a pencil eraser grain of sand will actually leave a visible streak across the sky as it burns up in the atmosphere. So this stuff doesn't need to be big to be visible. And this is a meteor shower. So this is the remnants of an old comet that you're actually seeing. And in general, we name meteor showers after the constellation that it appears to be coming out of. So for instance, in late August, there are the Perseids. That means that it's the meteor shower that looks like it would be coming out of Perseus. and that means that Earth in general is moving in the direction of Perseus at that particular time. So here's at least one really nice high-speed time-lapse video of that. But again, if you haven't gotten a chance to go out on a really dark night and see a very bright, distinct meteor shower, I definitely recommend the Perseids in the northern hemisphere. But again, getting away from all that light pollution is the key to seeing a nice one. It's really worth it. So those are comets, and now the question is, where do they come from? And it turns out that where comets come from is the best time to tell the story of Pluto. So you guys might have some sense of what this Pluto controversy is. Is it a planet? Is it not a planet? Well, it turns out that it was discovered with the best of intentions, and then Pluto basically just started getting on astronomers' nerves right from the get-go. So in the early 1900s, there were some observations of Uranus and Neptune that seemed to indicate that their mutual gravitational interaction was not enough to explain the wobble of their orbits. And people at the time thought, well, it worked once, it could work again. Remember that the existence of Neptune was actually predicted because of the wobble in the orbit of Uranus. And so now people said that, well, maybe Uranus's or Neptune's extra orbital wobble as it moved in the far part of its ellipse could be caused by a new planet. And people set out to find this planet. They even gave it a name before they found it, called it Planet X. And in 1930, an American named Clive Tombaugh found the new planet. This is Pluto. It was named by a school child in a contest, a name of planet contest, and I think the person who had the final say was named Percival Lowell, so the P and the L show up probably because he was a little bit biased towards that particular suggestion. This is in fact the best Hubble Space Telescope image of Pluto. We've now flown by it with Rendezvous mission, actually carrying the ashes of Clive Tombaugh on it, but you can see that this seems to be a very indistinct planet. And it turns out that Pluto is a little bit strange. So for one thing, Pluto is really small. So the smallest planet otherwise is Mercury, and then even Earth's moon, Pluto is much smaller than it. And in fact, Pluto also has a moon, an appreciably sized moon, almost on the order of the size of Pluto. So, you could ask the question pretty honestly, because Pluto doesn't even orbit, their shared center of orbit is actually outside of Pluto. So it's not like one's orbiting the other. It's almost like they're orbiting a point in space. They have such similar masses. And we'll talk about barycenters a little bit later when we get to binary stars. But you could almost ask the question, like, if we make Pluto a planet, why couldn't we make Charon a planet? It's quote-unquote moon, but that's fine. Pluto's just Pluto. It's being a little bit weird. If you look at its orbit, it's even weirder still. So the rest of the planets basically lie in the ecliptic, and they do have eccentricities. That's really important. It's the only reason that Kepler was able to make his breakthrough is the extreme eccentricity of Mars. But when I say extreme eccentricity of Mars, it's got nothing on Pluto's orbit. So Pluto is 17 degrees out of the ecliptic, and Pluto's orbit is also so eccentric that sometimes it's closer to the Sun than Neptune, sometimes it's farther from the Sun than Neptune. It's by far the strangest orbit of all of the planets, most inclined, most eccentric. But still, it's okay to have one weird friend. People basically forgave Pluto all of that stuff. But honestly, the thing that really changed was in the 1990s, more Plutos started to be discovered. And in fact, at like a pretty rapid rate. So this is the first of them. And the person who discovered Eris, which is farther out than Pluto, but bigger, and Eris has a moon or coplanet, whatever you want to call it, Dysnomia. And the person who named Eris is the Greek goddess of discord, I think they knew what they were starting, because a lot of discord actually did ensue. So there's one, and maybe, 10th planet, fine, we can deal with that. But it turns out that these things are really common. And in the decades since, this is just a sampling of them. More than 20 what are now known as Kuiper Belt objects and possibly dwarf planets, things that are very similar to Pluto in both the distance from the Sun and composition and orbital makeup and size have been discovered. And so this was it. Nobody wants to send their kid to school and, have them memorize like a 30 long planetary mnemonic. So what happened was in 2006, the International Astronomical Union got together and they figured out a way of redefining planet to make Pluto not a planet. And now what Pluto is a dwarf planet. And this picture actually kind of gets the point across. It just looks like it's snark, but the thing that makes Pluto not a full-fledged planet and a dwarf planet actually has to do with Pluto not finishing its lunch. So this is the definition of planet as of 2006. To be a planet, you need to do three things. You need to orbit the sun. You need to have enough gravity to squish yourself into a sphere. Like so Ceres has done that in the asteroid belt. And thirdly, and this is the one that discludes Ceres and discludes Pluto from being true planets, is that you have to have enough gravity to clear your orbital path of its debris. So it's not enough to have enough mass to squish yourself into a sphere so you look planety. You also have enough to sweep up all the debris in your path. And so you have a clear trajectory around the sun. And so that's the finishing their lunch part. And that's what Pluto hasn't done. So if anything doesn't satisfy the third criteria and just satisfies 1 and 2, orbits the sun and is spherical, they're classified as a dwarf planet. So now you have two examples of that. One is Pluto and the other one is Ceres in the asteroid belt. So don't feel bad for Pluto. Instead of being the weirdest planet, Pluto has now been, don't think about it as being demoted. Now Pluto is like the king of the Kuiper Belt. And the Kuiper Belt is the debris that Pluto wasn't able to clear. So that's the stuff that kept it from meeting criteria 3 of planethood. So it's basically like kind of if you imagine a squished donut of material, this is the Kuiper Belt. It's generally the stuff in the Kuiper Belt is pretty inclined. It's out of the ecliptic. It's probably pretty eccentric, their orbits. And the Kuiper Belt itself extends from Neptune to about maybe 50 to 100 AU. It's not really clear. And these dwarf planets like Makemake and Haumea, all the ones in that slide, and many more, are the largest elements of the Kuiper Belt. So the whole thing might include 50,000 to 100,000 other such things. And if you think about Halley's Comet, which starts at about Neptune and is very icy and comes in and bombs the sun in an eccentric orbit, Halley's Comet has a lot more in common with Pluto than it does with even Neptune or any other asteroid. So Pluto really does belong as a Kuiper Belt object. So the Kuiper Belt would be things that are comet-like in nature, like all of these things you could think about as dirty snowballs, probably with a lot more ices in the large Kuiper Belt objects like Pluto. So it turns out that can't explain all of the cometary visitations. And those comets that I showed you, one for instance, that will return in 17,000 years, that must be coming from even farther out than the Kuiper Belt. And secondly, there are some comets that, as inclined as Kuiper Belt objects can be, maybe like 20 degrees out of the ecliptic, there are some comets that visit us from almost directly above the sun's orbital axis, so 90 degrees out of the ecliptic. It's very strange. So because of these very oddball comets that come from very far away and come from huge inclinations, in the middle of the 20th century, two astronomers independently proposed that there must be this cloud of other stuff. Nobody's ever seen anything directly in it because it's so far away, but stuff comes from it, and therefore maybe we have this cloud of what could be billions, almost a trillion in some estimates, of objects, which is almost like an outer, icier version of the Kuiper Belt. And the person who got his name on it was actually the second person to propose it, Jan Oort, who's a famous Dutch astronomer. And the idea behind the Oort cloud, again, is nobody's actually seen it, but we've seen things coming from it. And the idea that, there are a trillion or, tens or hundreds of billions of things in it, it's the same idea as if you went out and you went fishing on a huge lake, and you caught 3 fish within 15 minutes. You would infer that there's a huge number of fish in the lake. So it's kind of a statistical argument. And the trillion sounds like a lot, but the Oort cloud is so diffuse that at this point we're sending spacecraft through it, and there's no chance that vanishingly small chance that they're going to interact with or hit an Oort cloud object. But this is the source of the very long period comets. And this is a schematic about what the Oort cloud must look like, which might seem a little bit strange, but when we talk about the formation of the solar system, how you might get this shell of stuff that reaches out almost 20% to the nearest star in this odd kind of walnut shell-like shape, will make a little bit more sense. So the Oort cloud probably looks like this. So if you notice, this is a logarithmic graph. So instead of linear distances add the same number, it's multiplied by 10. And 10 to the 5 AU is, again, about 20% to the nearest star. So this extends a very far distance. And the idea is this might have been formed in the early stages of the solar system, where material was thrown out through gravitational interactions or pulled in and spit out by the sun to form this very, very large halo of very diffuse stuff. So these are the long period comets, like the ones that come back every 20,000 or 15,000 years would probably come from out here, especially if they come from very high eccentricities outside of the ecliptic. Okay, so we're throwing around like 10,000 in the Kuiper Belt and a trillion in the Oort cloud. It really does sound like there should be a tremendous number of comets. And, we talked a little bit about where they go. The sun is a pretty good comet vacuum. There's the remnants of Shoemaker-Levy 9. You can see the scarring from where the parts of Shoemaker-Levy 9 plunged into Jupiter. So part of it is that there are a lot of comets, but they generally get pulled in by the stuff that has a stronger gravitational pull. So the outer planets pull in a lot of the comets and keep us safe, which is really nice. The sun will pull in a lot of comets. The more mass the planet or the sun has, the more likely it is to get hit. That's really nice. But then secondly, we've seen some that appeared to be in very stable Keplerian orbits, but then may have totally evaporated. So there are at least 2 meteor showers that have no associated comet. Nobody knows what the comet is that could have formed them. It could be that they just completely evaporated after hundreds of orbits, and this could have been, millions or a billion years ago. So in particular, the quadrantids, which show up in January, and the Delta Aquariids, these are worth mentioning because this is an example of the comet naming scheme. So Aquariids mean that you would see them as if they were coming out of Aquarius, which means the Earth is zooming in that direction. And the delta means that it's the 4th such meteor shower. So in fact, there were alpha Aquariids and then beta Aquariids and gamma Aquariids. The 4th meteor shower of the year coming out of Aquarius is the Delta Aquariids. But again, these don't have a comet, so it could have been that they totally evaporated. More likely it interacted with something and was eaten by a planet, maybe even Earth. Okay, so again, here's Shoemaker-Levy 9, and this is an infrared image. I'll leave this here if you want to watch the excitement that NASA scientists have when they get to observe potentially mass extinction causing comet get eaten by Jupiter instead of hitting Earth. And the other evidence we have of very frequent comet outer planet impacts is, again, our theory of the formation of planetary rings. So all of the outer planets have rings. Saturn's just are most easily observable and most beautiful and distinct. But the idea behind these is that material has come in and it gets captured by the planet, and then as it goes up and down through the ring, it's got to interact with the stuff. So it's almost like kind of a grinding down process. Imagine that you take a stone and then you pass it back and forth through sand for millions of years. You'll eventually grind down the stone. And this process is so efficient that the rings of Saturn in particular have this incredible aspect ratio of, 250,000 kilometers across and, in most cases, much less than a kilometer thick. So what this material was, or it keeps getting replenished by, are captured comets. So lots of comets, but lots of defense mechanisms for Earth. Obviously, it doesn't always work, and we do get hit by comets. Some of the famous impact craters or sites which could have been comets, only one is known to be, are the Yucatan Peninsula site, which ended the age of dinosaurs, that has no no uniquely distinct asteroid-like fragments, so it's unclear whether or not it was an asteroid or a comet that hit us. And this, the Barringer crater, it's got in Arizona. This is from an impact about 50,000 years ago, and you can see there's a little mining colony down there. What they wanted to do is find the really metallic iron meteorite that hit and sell it for $1 billion or whatever the ore was worth, and they found nothing. So it could have been a comet. If a comet comes in and evaporates, it leaves nothing but volatiles and gases and kitty litter, so nothing of worth. And the one that we know to be a comet is the Tunguska Event. Within a year, people had trekked out to the impact site and looked for any evidence whatsoever of metals or basalty volcanic rock or the sort of carbony burned remnants that would come from an asteroid, and nothing. So if you see, swamp, who knows if that water was from a comet or if that water was from Earth already. So secondly, we have some very indirect evidence of Earth being hit by comets insofar as if you just look at how a terrestrial planet should form at our distance from the sun, it's really hard to make a terrestrial planet that has oceans. In fact, if you look at the rest of the terrestrial planets, there's not an ocean in sight. Melt all of the polar ice caps on Mars, and in fact what they are is dry ice, they're frozen carbon dioxide. So the small amount of water on the moon or on Mars is actually not enough to make an ocean. So it turns out that one of the best theories about how you get a liquid ocean on a terrestrial planet like Earth is that if we were bombarded by comets early on in the formation of the solar system, and after we formed, we were really hot, we've cooled down, and after we cooled down enough to not evaporate the water, comets came back and bombarded us and released all of their volatiles. And so the evidence, which isn't 100% clear that our oceans are actually from cometary impacts, is so-called isotopic evidence. So if you look at the ocean and do a census of water molecules in the ocean, you'll see that most of it is normal water, H2O. So there are 2 hydrogens and 1 oxygen, but some of it, a really small proportion of the water, is what's called heavy water, where there's 1 oxygen, 1 hydrogen, and then 1 heavy hydrogen, or deuterium. And the only difference in between the heavy hydrogen or deuterium and the normal hydrogen is this has an extra neutron. So this doesn't happen a lot. That's why heavy water is so expensive when you use it for engineering applications. But you can take that isotopic ratio and the fraction of water that's heavy water, and it almost acts like a fingerprint. And so recently people have been able to look at the same fractions of regular water to heavy water in comets, and they seem to correspond. So it's almost as if our oceans bear the isotopic fingerprint, the correct ratio of heavy water, to indicate that they were from cometary impacts. Thanks, comets. So how do we know all this stuff? We've talked a lot about it. Historical sources actually work really well because comets are such dramatic events that humans record them. So there are comet sightings that go back thousands of years. We actually can use the same idea of looking at them and using spectroscopy, which is analyzing the type of light. We'll talk about this a lot once we get to the sun, and it'll actually be the primary tool of astronomy for the second half of the course. So don't worry if you don't 100% understand spectroscopy yet. But the idea is each type of element actually gives off its own particular type of light, so you don't have to go and grab a bucket of comet and melt it and see that there's actually methane in it. You just have to know what methane looks like when you get it really hot and it starts emitting light. But we actually do go out to comets. It's happened a few times, and I'll just pick 3 representative missions. And they kind of bear the cultural hallmarks of who did them. In 1986, the Italian Space Agency actually was headed by an Italian group, sent a spacecraft out to Halley's Comet and took a bunch of beautiful pictures. It was a really Italian thing to do. The European Space Agency headed a project in 2004 called Stardust to collect some stuff from Comet in a very sticky special trash can. Very European thing to do. And in 2005, NASA, the American space program, built a spacecraft that flew out to a comet, Tempel 1, and detached into two parts. One part took pictures, and the other part hit the comet as hard as possible. So we bombed a comet, and this is actually some of the pictures from the Tempel 1 impact. And the second part analyzed the debris and the light coming off of it. So pretty American thing to do. In fact, they did it on the 4th of July. So here's some videos that show the Tempel 1 impacts. So these are stills from the observation craft, and the thing is about the size of a dump truck that went and hit the comet. It's actually pretty neat to see, bombing an astronomical object. And as always, key terms and key ideas. And I will say one more thing, that we're about at the last place in this class where we can talk about actually doing that. So sending spacecraft out to actually interact with things, even just fly by and take pictures, let alone bring back samples. So we'll talk a bit about the process of doing that and a really brief history of spaceflight, because from here on out, it's going to basically be passive observation because stars are way too far to get to.